It's 2:14 a.m. on a Tuesday, and your phone starts buzzing. It's a PagerDuty alert. Your production system just went entirely pitch black. You open your laptop, pull up the dashboards, and see absolute chaos. API latency has spiked from a snappy 40 milliseconds to an agonizing 30 seconds. Your primary Postgres CPU is pinned at 100%, and the app server logs are spitting out a single repeating message. Fatal. Sorry, too many clients already. When you see that error, your first instinct is to dive into the database configuration file and bump the connection limit from 100 to 1,000. Doing that is exactly how you make the outage worse. To understand why, look at how this hardware actually operates. Every single database connection you open is not a lightweight variable sitting in memory. In engines like Postgres, each connection spawns its own dedicated process. That process claims real physical RAM for query working memory, sort buffers, and overhead. When 500 web requests hit your backend at once and attempt to open 500 raw TCP sockets to the database simultaneously, the hardware chokes. The CPU spends almost all its time aggressively juggling these processes back and forth, a failure state called context switching, rather than executing the actual data queries flowing through them. The fix for this memory crisis is a connection pooler, like PG Bouncer. It sits right between your web server and your database and acts as a strict traffic control layer. It maintains a tiny, highly efficient pool of, say, 20 persistent connections. When a massive traffic spike hits, the pooler catches the threads, funnels those 500 requests into a microsecond waiting queue, and reuses the active connections the instant they finish processing. By intentionally bottlenecking direct hardware access, the CPU executes those queries at maximum cache efficiency. Deliberately restricting your database connections actually makes your application run faster. The pooler brings the system back to life. You go to sleep, but as the clock strikes 9 a.m., the database locks up again. You check the active query logs to see what's happening. There it is, a massive single SQL query, run by the internal marketing team's new business intelligence dashboard. It is trying to calculate customer lifetime value across 10 million rows at once. This crash exposes an architectural conflict that trips up teams constantly: the difference between OLTP, your main production database, and OLAP, your data warehouse. This diagram shows exactly how they differ. OLTP stands for Online Transaction Processing. Its storage looks like this, row-oriented. It is highly optimized for lightning-fast single-record operations, like updating an individual user's shopping cart. It reads and writes entire rows as single blocks. OLAP stands for Online Analytical Processing. If you want to aggregate millions of records, the architecture pivots sideways into a column-oriented layout. When calculating total revenue, the database scans only the specific revenue column, entirely bypassing the grayed-out data like names and addresses. Forcing your production OLTP database to run a heavy OLAP aggregation forces the hardware to read millions of full, unnecessary rows off the physical disk into memory. This instantly evicts your application's hot cache data and kills the live system. Analytical and transactional workloads must be physically segregated. Eventually, your product grows. The immediate fires are out, but your main events table hits 100 million rows. Write operations start to slow down. The engineering team gathers in a room and starts throwing around terms like sharding and replication in a panic. Stop. These three terms describe completely different architectural strategies. Applying the wrong pattern to your specific bottleneck guarantees a disastrous system layout. Let's look at how each one actually functions. First is partitioning. This happens inside a single database instance. It takes one massive table and splits it internally into smaller, physical chunks based on a specific key, like date ranges. When you query data from a specific year, the engine instantly bypasses 90% of the mini-tables. It solves disk scan latency, but notice a hardware boundary. You are still entirely bound by the RAM and CPU limits of a single physical machine. Second is replication. This strategy uses multiple machines by asynchronously copying your entire primary database outward to several independent read replica nodes. Your web application distributes read-heavy traffic seamlessly across the replicas, providing massive read scale and failover redundancy. However, it fails completely at alleviating write bottlenecks. every new user signup and data update still hammers that single primary node. Third is sharding. A router proxy sits in front of your system, analyzes incoming write traffic, and distributes it horizontally across entirely independent primary database servers based on a shard key, like user ID ranges. Sharding solves the hardware limits of both partitioning and replication. It provides theoretically infinite scale for both reading and writing data. Warning tone. But the operational penalties are severe. Cross-shard joins become incredibly difficult. Distributed transactions require complex coordination, and rebalancing data when a single server fills up is an operational nightmare. True architectural maturity means exhausting single machine partitioning and read replication before you ever accept the extreme complexity of horizontal sharding. Before you blindly rewrite your backend in Rust or shard your database at the very first sign of a latency spike, you need to investigate your core architecture. This diagram is the senior architect checklist. Verify that a connection pooler is active in front of your database. Ensure heavy analytical OLAP queries are completely isolated from your transactional OLTP tables, and thoroughly test table partitioning before taking on the burden of sharding. If you are building a system right now and dealing with performance bottlenecks, drop your exact database stack and table sizes in the comments below. Let's diagnose where those bottlenecks are hiding. Surviving a massive outage is about understanding memory allocation and traffic patterns, not throwing infinite hardware at industry buzzwords. If you want to see how we implement these clean architectures in production, check out my app, TBRLY, linked below. Subscribe, and I'll see you in the next teardown.